Okay, this is going to be our second and final video on fluid statics. And so I only have two sort of big topics I want to talk about in this video. The first one's going to be Pascal's principle, and the second one's going to be Archimedes' principle. Okay, and so we're going to talk about a few things. We'll do a few examples, and this will finish up our section here on fluid statics. And for our 101 course, this is going to bring us to the end of the course here. Okay, so let's get started. Let's remember that pressure is defined as a force per unit area. Okay, so thinking in terms of pressure as a force per unit area, if we have an enclosed fluid, so we can imagine a fluid in a piston or something like closed on all sides, right? If we apply a force to that fluid, well, our fluid, the particles which make up the fluid are still free to move around, right? So as we apply a force to the fluid, each of these particles can move around, and it sort of disperses the force evenly throughout the entire fluid, right? So the fluid will transmit this pressure applied to it to all parts of it undiminished, right? And basically, this is just what Pascal's principle is telling us. It's telling us that a change in the pressure applied to an enclosed fluid transmits that pressure, or that force in a sense, to all portions of the fluid and to the walls which are containing this fluid, right? So that's Pascal's principle. And if we apply Pascal's principle to a hydraulic system, like a very simple hydraulic system like the one we see here, this is from the textbook. I don't remember exactly what figure this is. Maybe I could look it up here. Let me grab it. So this is figure 11.12 from the textbook. And so what does this sort of tell us? Well, we saw that we can write our pressure as a force per unit area, right? As we see here, pressure is force over area. So we know that pressure 1 here in our first piston is going to be equal to the force applied times, or over, I should say, the area of the piston, like the disc, the surface area of this disc that we're applying the force to, right? And we know that's true also for piston number 2 here, but they're also connected, right? And Pascal's principle tells us that P1 has to be equal to P2. And because that's true, that allows us to build this sort of interesting relationship here, excuse me, where we have F1 over A1 is equal to F2 over A2. Okay, and it's pretty straightforward, right? It's not overly mathematically complex, but this simple relationship is going to give us a sort of handy tool for solving, a number of problems where we have fluids under pressure. Okay, and so we'll look at one example of that right now, and this is a sort of simple car braking system. Okay, and this is an example from the text also. This is 11.6. I'm going to pull up 11.6 here so that I have the numbers. Yes, I have them here. And so what are we looking at here? We have a car. This is basically the car's braking system. We have the brake pedal here, which a person would step on, and this would apply pressure to a piston, which would this would basically apply a force to a piston, which would apply pressure to this liquid in the hydraulic system, this fluid. And this fluid would then, through Archimedes' principle, or I should say through Pascal's principle, would disperse this force throughout the fluid, right? So we step on the brake pedal, pressure is applied to our fluid, and this pressure then applies a force to the pistons at the brakes. These are supposed to be our disc brakes, and we can imagine there are some brake pads here. And then so we apply this pressure, which then turns into a force applied to our brake pads, which then stops the car for us, right? And so we can do some calculations relating to this. So here we go. We have a force of 100 newtons is applied to the brake pedal. So this is 100 newtons being applied to the brake pedal here. Now we're going to kind of gloss over the why this 100 newtons applied to the brake pedal turns into 500 newtons into this F1 here. We could do this calculation here, but this would be a calculation using our equilibrium conditions, right? This would be back from a couple of modules ago when we were looking at our two equilibrium conditions, and we could calculate if we applied a force here. We could look at the torque. We could use this as our pivot and so forth. But we're going to skip all that. We're just going to take for granted that we can calculate it, and we're going to say that F1 is equal to 500 newtons. So we have 500 newtons pushing down on our piston here. And so this piston here, this is called our master cylinder. So we have a force being applied to our master cylinder. Then the pressure created in the master cylinder is transmitted to all of our slave cylinders. These two or four in a usual four-wheel car would be called our slave cylinders. And so we have our pressure being transmitted, and so there's a force applied on these pistons, which is then used to stop the car, right? And so we're given these dimensions. We're told that the diameter of our master cylinder is 0.5 centimeters, and the diameter of each of our slave cylinders is 2.5 centimeters. And so we want to calculate F2 if we know that F1 is 500 newtons, right? And so I guess fairly obviously, because we just derived this relationship up here, this simple relationship between the force and the area of our two different pistons, we're going to use that expression. So we have F1 over A1 is equal to F2 over A2, and so let's rearrange this slightly. We want to find F2, so we're going to have F2 is equal to A2 over excuse me, A1 times F1. Right, so this is just me isolating. This is basically just me multiplying through by an A2, and I just rearrange a little bit on the left and right here. But we know what these areas are going to be, right? We know that these cylinders are actually just basically like circles, so they're going to have the area of a circle. So that's going to end up being pi r2 squared over pi r1 squared times F1, right? And so these pi's will cancel, obviously. And I guess we can just go straight ahead with the calculation here. We know that the radius. So we're given these diameters. I'm not sure if I said radius before or diameter, but we're told that these are diameters. So we have to be careful. We're going to take a look at our area 2. So our radius 2 is going to be half of our diameter 2. So we're going to end up with 1.25 centimeters. Excuse me, squared over 0.25 centimeters squared, right? And this is going to be times 500 newtons, which is our F1. All right, and if we do this calculation, we're going to find that our F2 is equal to 1.25 times 10 to the 4 newtons. Okay, so we apply this 100 newtons of force, which through this lever here gives us 500 newtons of force applied to this fluid, increasing the pressure in the fluid, which transmits, in a sense, this force through the hydraulic system, and then we get this F2 out the other side of 1.25 times 10 to the 4 newtons. Okay, and so that's sort of a demonstration of a useful way that we can apply Pascal's principle in hydraulic systems. But maybe the key takeaway message from this sort of section is just remember this equation here. Just remember that if you apply a pressure to a fluid, Pascal's principle tells us that this pressure is transmitted undiminished over the entire sort of volume of the fluid. Okay, so that's Pascal's principle. We're now going to move on to Archimedes' principle. And so when we're thinking about Archimedes' principle, generally we want to have in our minds, we're thinking about things floating, the buoyant force, objects floating in water, things like that. Okay, so let's start off here. The fact that the pressure increases with the depth in a fluid means that the upward force on the bottom of an object in a fluid is going to be greater than the downward force on the top of an object. So I didn't include the sort of full discussion from the text here. They have a couple of nice diagrams in the text that you might want to take a look at, namely figure 11.19. So maybe I'll quickly draw it in the solution area, and I'll erase it after. But basically, you end up with, so imagine we're in some kind of a large container here full of fluid, and we have some sort of an object here that's fully submerged, right? So this is like water or something. Okay, so because the pressure increases with depth, and because this pressure is applying a force to all parts of the object that's being submerged, we're going to end up with a larger force because this bottom part is deeper. So ignore these two little arrows. Because this bottom part is deeper, we're going to end up with a larger force on the bottom acting upward than we do on the top acting downward, right? And it's this sort of difference in these two forces that's going to give us our buoyant force. Now I got to get rid of this. If you guys want to see the drawing that accompanies sort of that discussion and maybe a little more detail on that discussion, you can see that in figure 11.19 in the textbook. But I haven't left space for that here. So basically, we're just going to sort of discuss the result of the discussion that we would have had about these unbalanced forces. In the end, what it ends up telling us is that Archimedes' principle, through this understanding of how the buoyant force works, tells us that the force, this buoyant force, this FB, is going to be equal to the weight of the fluid that is displaced by whatever this object that we're submerging is. Okay, so again, more of a discussion in the textbook, but the takeaway message is this equation here. Buoyant force is equal to the weight of the fluid. So this is basically the force of the gravity, that would be experienced by this fluid that's being displaced. Okay, and we maybe the easiest way to get a handle on this is to do another example. So let's jump into the example here. Excuse me. So what are we doing here? We want to calculate the buoyant force on a 10,000 metric tons, so 1 times 10 to the 7 kilogram block of solid steel, so completely submerged in water. Okay, so it doesn't really matter what the shape is, but it's basically some sort of a compact shape, ball or a cube or whatever. Basically, whatever the shape is, as long as it's totally submerged in the water, we can do this calculation. Okay, so we want to calculate what the buoyant force on this is in part A. And so how are we going to do that? Well, we're going to remember that our definition of density tells us that the density is equal to the mass over the volume, right? But we're interested in the volume here, right? We want to find the buoyant force, and to be able to find the buoyant force, we need to find out how much water this thing is displacing, how much fluid we're moving around. And so to be able to find out how much water is displaced, we need to find out what the volume of this block or ball of steel or sphere or whatever is, right? So let's rearrange this so we can find the volume of steel. Okay, and the volume of steel is going to be equal to the mass of the steel over the density of the steel. Okay, well, we're told right away, originally in the statement of the problem here, that the mass of the steel is 1 times 10 to the 7 kilograms. We could look up the density of steel. I don't have it in front of me, but this value would have come from the table, I think it's table 11.1 in the textbook, that has all these different densities of different materials. So if we look it up there, we're going to find that that steel has a density of 7.8 times 10 to the 3 kilograms per meter cubed. Okay, and if we do that calculation, we're going to find that we have a volume of 1.28 times 10 to the 3 meters cubed. Okay, so that's our volume of steel, and because we know this thing is fully submerged, as this thing goes underwater, how much water is it displacing? Well, it's clearly going to be the same volume of water as the volume of steel, right? and so we can calculate what the mass of that water is going to be. So we can calculate the mass of the water that's being displaced. We know that through this relationship up here, the mass is going to be the density of water times the volume of water that we're moving here. But the volume of water is just the volume of the steel object that we're sinking in it, right? So let's look up the density of water, or we should probably remember what the density of water is. That's just 1 to some degree of certainty here, 1 times 10 to the 3 kilograms per meter cubed. And we're going to multiply that by the volume that we found above, 1.28 times 10 to the 3 meters cubed. Okay, so if we do that calculation, we find the mass of water is going to be equal to 1.28 times 10 to the 6 kilograms. Okay, so as we sink this steel object in the water, we're moving 1.28 times 10 to the 6 kilograms of water. That's how much water would have, or the mass of the water that would have occupied the space that this object has now taken up in the water. Okay, and so we're interested in the buoyant force, or FB, right? FB. But Archimedes' principle tells us that FB is equal to the weight of the water that we're displacing here, and we know that we know that FG is just equal to mg, and this is basically our FG. So we need mg. It's the mass of the water times g, and we can very quickly do that calculation. Also, that's just going to end up being 1.28 times 10 to the 6 kilograms. And this is going to be times our gravitational acceleration. Okay, and if we do that calculation, we find a buoyant force of 1.3 times 10 to the 7 newtons. Okay, and so if we compare that to the weight of the steel, well, we know that the weight of the steel, so weight of the steel, is going to be equal to the mass of the steel times gravity, right? And so if we do that calculation, what do we have here? We have 10 to the 7 kilograms. So we have 1.00 times 10 to the 7 kilograms times gravity, 9.80 meters per second squared. So if we do that calculation, we find 9.8 times 10 to the 7 newtons, right? So we see that the weight of the steel is significantly greater than the force of buoyancy keeping it up, or trying to keep it up, and so we have a net acceleration downward, right? And so this thing will sink, right? And so we can certainly do more stuff with this, but we're not going to have time in this course. We could then say something like, okay, so we have a net acceleration downward, but there's going to be some drag force as this thing is accelerating downward in this fluid, right? So there's going to be some drag, very similar to the way we did air resistance or drag in earlier chapters. I think it would have been module 4 that we would have done it in, but we're not going to have time for that. So basically, we've calculated here that our force of buoyancy is going to be less than the weight of the steel object. This thing will sink. There'll be some acceleration downward, and we're just going to leave it there. Okay. In part B, what is the maximum buoyant force that the water could exert on the same steel if it were shaped into a boat that could displace 1 times 10 to the 5 cubic meters of water? Okay. So let's take a look at part B here. Oh, and I haven't left very much space, but we probably won't need too much. We'll try to write kind of small. And so what do we kind of want to do here? We want to find the maximum buoyant force, right? If we shaped this thing, so basically we're taking this block of steel and we're reshaping it into some sort of a boat-like shape, right? So we smash it down into a boat-like shape. we need to know what the mass of water that we're going to be displacing with this new volume is. So we're going to end up, we need to do this calculation. We need the mass of water, which we know is going to be the density of water times the volume of water that we're displacing with our boat here, and the maximum, meaning, so we're looking for the maximum buoyant force, right? And so this would be like if we sink the boat, we push down on the boat as much as we can until it's basically fully submerged, but not filling with water, right? So if we do that, we're going to end up with, well, we start off with our density of water. Okay, and now the volume of water that we're going to be displacing, well, that's simply the volume of our new boat-shaped ball of sphere, or ball of steel, I should say. Okay, and if we do that calculation, we find, I'm going to drop the decimals here, or maybe I won't. Okay, so we find 1 times 10 to the 8 kilograms. That's how much water will be displaced, or the mass of the water, I should say, that will be displaced as we push this boat into the water, to the sort of right where the water is, to the brim of our boat, right? Okay, and so we need to know what the buoyant force that this boat is going to experience as we're doing this. So how much force is the water pushing up on the boat with, basically. And we're going to have, again, just from our discussion here on Archimedes' principle, we know that our buoyant force is going to be equal to the weight of the water. Well, that's just going to be the mass of the water times gravity. We just calculated the mass of the water. That's 1.00 times 10 to the 8 kilograms. And we know that our gravitational acceleration is 9.8 times, or no, 9.8 meters per second squared. And so if we do that calculation, we will find a buoyant force of 9.8 times 10 to the 8 newtons. Okay? And so that's a quick sort of look at how we can use Archimedes' principle, and how we can use this expression here to calculate buoyant forces, sort of depending on the weight of whatever fluid it is we're displacing, and we can sort of see how that works here. But we can also go further with this idea. We can go further with this idea, and we can discuss density and Archimedes' principle. And this is going to bring us kind of to the very, very last subject we're going to talk about, which is specific gravity. And we'll do one example with that, and that'll kind of close this all out. Okay, so let's start off here. We have density in Archimedes' principle. So the average density of an object is what determines whether it's going to float or not float, right? So if the average density of the object is less than that of the surrounding fluid, it's going to float on top of the fluid, right? Like we saw with the steel that we worked with before. When we crumple this thing down, all of its mass is in a small sort of volume, so its density is high, and it sinks. When we kind of unfurl it and build a boat out of it, well, we still have the same mass of steel, but now it's shaped in such a way that its average density is less, right? Because the average density takes into account the hull of the boat, but also all the sort of empty space inside the boat. And so now this thing's average density is lower than that of the water, and it floats on top of the water, right? So so we can kind of see how this whole relationship works out, and we can calculate what the fraction of an object that's going to be submerged is. So a boat sits in the water. Some part of it sits below the surface of the water, and some part of it sits above the surface of the water, right? We have water here, and we have our boat. It sits something like this, right? So some of it will be below, some of it will be above, right? And we want to calculate the fraction that is submerged, right? And so how do we do that? Well, we can see the sort of way that we derive our equation here. We start off, we're looking for the fraction that is submerged. We have the volume of the boat, or whatever, the object that is submerged, over the total volume of the object. And that's going to be equal to the volume of the fluid over the volume of the object, okay? And we know that we can rewrite, so why are these equal? Well, clearly the denominators are going to be equal because they're the same thing. The numerators are equal because however much of the object we submerge, well, that's the volume of water that's displaced by this object being submerged, right? And so we can rewrite each of these volumes in terms of their masses and their densities. So we have the mass of the fluid over the density of the fluid, and we have the mass of the object over the average density of the object. So I've put this bar over here just to emphasize that we're talking about the average density of this object, right? So we have to be careful, because if we have a boat, we're not just talking about the density of the steel that makes up the boat, but we're talking about the average density of the steel and all the air inside the boat. So it's somehow much less dense than it would be if we crumpled the whole boat up into a solid sphere and then sank it, right? And so we can clean this up. We're going to find that we can sort of simplify this whole thing, and if we do that, basically what we're going to find is that the mass of the fluid that we are that we're displacing is going to be equal to the mass of the object, and so we can rearrange this and find this relationship here. And so if we clean the whole thing up, we're going to find that the fraction of the object that we have submerged is going to be equal to the average density of the object over the density of the fluid in which it's being submerged, right? And so we can make use of this relationship to measure the density of objects that we don't want to start sort of weighing directly. We can just start floating objects over some sort of a fluid, and if we see how far they submerge, we can right away tell what their density is, right? And this leads us to this idea of specific gravity. And so specific gravity is the ratio of the density of an object to a fluid. And usually we use water for this type of thing, so we've defined it here with water. So our specific gravity is the average density of whatever the object we're trying to measure is over the density of water, okay? And again, this is assuming we're using water. It could be some other fluid, but in this case it's going to be water. This brings us to our sort of final example here. Sorry about that. And so, here, let me just mute myself for a second while I clear my throat. Okay. All right, so in this example, we want to calculate the average density of a floating person, okay? And so I think I have numbers for this somewhere here in the text. This is directly from the text. This is 11.9 from the text. I've slightly modified it just to make it a little simpler to write down, but basically this is it. So suppose we have a 60 kilogram person floating in fresh water. 97% of their volume is submerged when their lungs are full of air. What is the person's average density? Okay, so we want to find the person's average density when their lungs are full of air, obviously, right? Because we're doing this measurement when their lungs are full of air, right? So we just want to find what the average density of our object is. So we know that the fraction submerged is going to be equal to the average density of our object over the density of our fluid. Okay, and so we can rearrange this. I'll maybe abbreviate this. We're going to call this. I'm just going to call this F. I'm just going to call this rho bar, and this I'm going to keep rho fluid. Okay, and so if we do that, we can rearrange this into the following expression. We're going to have our average density of our person is going to be equal to the fraction submerged times our density of our fluid. Okay, and then really we're just at the point where we can sum in numbers and get our solution. So we're going to have the average density of our person is going to be equal to, well, the fraction submerged, that's 0.97, right? So 97% of the person is submerged, times the density of our fluid. Well, this is the density of water. This is 10 to the 3 kilograms per meter cubed. And if we do that calculation, we find out that, that this person has an average density of 970 kilograms per meter cubed. Okay, and that would be the answer to a question like this. So this pretty much finishes off this chapter, this module, and so we can see that there wasn't a lot of sort of very complicated manipulations that we needed to do for most of these problems. That's kind of how these problems go. This is more of an introductory module. Usually at this point we could go into more complicated calculations. Like this would be just setting the stage so that we understand some of these variables and how to work with them, and then we would start doing more complicated stuff. But since we're at the end of the course, we're only going to look at a very sort of simple sort of overview of these values as we did in this chapter, and I think you guys will find that the assignment is probably fairly easy compared to some of the ones that we've done more recently, where we were able to use the sort of full force of all of the terms in mechanics that we sort of built up. But now since we're starting out fresh in fluids, you're probably going to find that the assignment is somewhat easier, right? Okay, so I'll leave it there for now, and I'll get the assignment out here shortly.